Hey folks, I'm gonna solve all problems before the contest for the upcoming 3rd Division Codeforces contest. Are you interested to join me and see my solutions and how I attack problems and how I code them and solve all problems together? I'm interested too. So let's start solving problems. Let's start this problem A. So this problem is asking us find the source number that resulted to x after k times. You can see an example here which 21 converts to 4 after 5 times. So first thing to pay attention is here it wrote print any possible initial value. Why? Because the answer is not unique. For example, answer to the first test case can be 8, 2. Why? If I have 8, let's say I have 8, this number is even, and then it converts to 4 after one step, right? So what does it mean? It means that answer can be 8, 2. Or here, you can see that answer for 5 and after one step is 10. But this one is unique. There is no other answer. But let's see this one again. So 21 after 5 times converts to 4. This is true. But also 128 converts to 4, 32, 16, 8, and finally 4. You can see that 128 is also an answer for the third query. So I think that you discovered the idea. We'll multiply our number by 2k times, and we can make sure that the number we achieve will lead to x after k steps. So what we are gonna do, so the answer is x times 2 times 2 times 2 k times. And this is x times 2 to the power of k for sure. So let's start coding it. So first we need to get the number of test cases, and then we'll go over all of the test cases and we get k and x from the input. So there are two ways here. First one is multiplying x by 2k times and finally printing x. So this is one way, and if you run you can see that it produces what we wanted to produce. And yeah, let's submit it. So this is this. Also we can make it shorter with writing it like this, and this is also a correct answer. Let me submit it again, and you can see a result of both of them. So this is for problem A. So while it's judging, let's review what we did. So what we did was making sure we make x times 2 times 2 times 2, and each step one of its 2 removes, and finally we will have x, and you can see we got AC. Let's solve problem B. So problem B has 2 new definitions you may not know. First is permutation, which is defined here. This is an, let's say, array of size n. These numbers 1 to n and like shuffled like this. 1, 2, 3, 4, 5 is a permutation, but 1 to 2 is not a permutation. And also it has another definition which is GCD, which is the greatest common divisor. You can read about it. So it's telling us, it's asking us actually to find to find 2 permutations with this combination. So what I'm gonna do is a trick actually. So Do you remember you were trying to find the sum of 1 plus 2 plus blah blah blah, 3, 4, 5 to n in elementary school? So how they taught you that answer is n times n plus 1 divided by 2. How? For us, they told us that let's write the numbers in the reverse order like this, and this will be n plus 1 cos n plus 1 plus n plus 1, and finally n plus 1. And this is n times n plus 1. But we counted the sum twice, so we need to divide it by 2. So given that, what we need to do is match each p with, let's say, its complement. Something like that. So what does it mean? It means that, for example, here, 1, 3, 2, okay? 1, 3, 2. So we can make 1 complete with 3, 3 with 1, 2 with 2, and the result will be 4, 4, 4. And for sure, GCD will be 4 always, and it's more than 3. And as you can see, n is at least 2, so GCD will be at least 3, and that's it. So yeah, let's implement what we talked about. So first, let's take the input, then let's get p, and finally let's print n plus 1 minus x for x in p. And I think that's it. 3, 1, 2. Yeah, that is what I had in my mind. Let's submit problem B. While it's submitting, let's review what we did again. What we did was making every P complete with matching some Q to it that we are sure that will make this sum equal to n plus 1. And as all of the Pi plus Qi will be n plus 1, so GCD of all these numbers is gonna be n plus 1 always. So we are still waiting for George. I'm not sure how much we need to wait, but yeah, soon we'll solve problem C, and there you can check out this problem got AC2. Let's solve problem C. For solving this problem, we need to consider 4 cases. A is even or odd, B is even or odd. I suggest you to pause the video right here, think, try to solve each case separately and come back. But yeah, let's think that you already did that. I'm gonna solve problem C for you now. So yeah, let's solve problem C. Let's solve problem C, and how we can solve problem C. We start with what I said. Cases. Let's start with the easiest one, where A is odd, B is odd too. I convert B to 1, A to A times B, so I divide B by B, and then I multiply A by B, and the result will be A times B plus 1, which is the maximum possible. Why? When you want to, when you have 2 numbers, and you can divide one of them with K and multiply the other one with K, the best case is you try to make them as far as possible, like make B as small as possible and A as large as possible. So this is the answer for this case. Then let's consider B is odd, A is even. The answer is -1. Why? Because B will always remain odd and A will always remain even. So answer is -1. Another case, A is even, B is even too. In that case, I convert B to 2 and A 2a times b divided by 2, and answer will be 2 plus ab divided by 2. Last case is when a is odd and b is even. In this case, I try to convert b to 2 and a to a times b divided by 2. But it's possible that this sum is not even. Why? Because there is a case that b has just 1, 2 in its factors, and this number will become odd, and finally odd plus even becomes odd, and the result is not even and not acceptable. But if it's acceptable, the answer is 2 plus ab divided by 2. Let's code it. Let's code it, and yeah, we will do it exactly from what we wrote here. We start from the reading input a and b, and if a is odd and b is odd, to print a times b plus 1. If a is even and b is odd, print -1. And note here, this is same as writing this, so I just write it. Then consider the case that both are even. If both are even, print 2 plus ab divided by 2. Finally, check if a times, or simply check if b divided by, if b is divisible by 4. If this is the case, again print this, or simply we can move this above to make this, and finally else print -1. And yeah, let's run. -1, 6, 58, 74, -1, 40. That's correct. That's correct. Let's submit. Problem C. Let's choose our code and then submit. Problem B is still in queue. So I think that our submission for C will remain in queue, but no worries, it will get AC. You will see it later. Let's solve problem D. For solving this problem, what I do is maintaining a candidate for each BI, for each value of BI. Let me start this solving some cases first, and then you will see what do I mean. Okay. Let me remove and clean the board to start. And yeah. Easy case. Consider 1, 1, 1, 1. What can we do? We can say 1, 2, 3, 4, right? Okay. Now, consider 1, 2, 2, and then 1. We write 1, 2, 2, and 3. First of all, okay, let me count this some more examples. Let's have 3, 3, 3, 1. I can do 1, 1, 1, 2. So let's iterate from left to right. When I see a value, let's think about this is array B. I'm iterating from left to right. I see number X, and I'm filling array A at the same time, and I want to know what to write here. Okay? So, the number X, consider the case, the easiest case. Consider X is not appeared before in array B. What I do is just setting a new number which is not used yet in A here. So what I need to do, let's say, is having some number m, which at the beginning is 1, and when I want to have a new number I didn't use before, I write m here and then do m plus plus. Or consider the case that x appeared before. This is x. So I will copy paste the number I wrote here, let's say y, to this cell, to this index 2. Unless in a case that x is already satisfied. What do I mean by satisfied? So let me show you. So let's go back to 3, 3, 3, and now let's see 2, 2 example. 3, when I see 3, it's the first time I see this. I assign 1 to it. Then, okay, let me make this example larger by adding 3 more 3s here. Okay, now I have 1, right? So when I want to write something here, I copy paste what I wrote here to this. So this is 1, 2, and this is 1, 2, and now 3 is satisfied. What does it mean? It means that now I have 3 3s. So it's satisfied. No more 3s are needed. So I see 2, I write 2, so m plus, and so I used m here and again here, and I plus plus m here. So 2, then 2, and 2 is satisfied now. Then I see 3, but I won't copy this number to here. Why? Because 3 is already satisfied. What I do is coming with a new number, which is m, 3, and then I copy paste it to here and then here. And again, it's satisfied. So you can see that all of the numbers are satisfied now, and the answer is this. So, okay, let's go back to what we were talking about. So first of all, make another array that is, make 2 arrays actually, that shows the current count of each value of BR. First of all of them are 0. And also record the candidate you have for that value. All of them are, you can fill them with arbitrary number, no matter, it's not important. So let's start from left to right. When you see a x, come here, check it out. If x is already satisfied, by satisfied I mean count is 0, convert count to 1, write m here as its candidate, do m plus plus, and move on. Otherwise, if x is not 0, use its candidate to fill your current index, increase the count by 1 plus plus, and then check if count of x is now x. If that's the case, reset the count to 0. Continue this. If after of all operations, all of the numbers are satisfied, that's it. Otherwise, answer is -1. Let me show the code, and I'm pretty sure you'll understand the solution. So let me start this getting n, then array b, then let me make array cnt, which is zeros everywhere, candidate, which is zeros everywhere, and let's make array a. Let's iterate over x's in b. If cnt of x is 0, let's define m, which is 1. If cnt of x is 0, append m to a, m plus plus, and now cnt of x is 1. else, add 1 else, append the current candidate of X to A and add 1 to CNT. Finally, check if CNT of X is equal to X. If that's the case, set it to 0, and that's it. You don't need to reset candidate actually. That's not a problem here. You don't need to reset candidate because when CNT is 0, candidate value will not be used anywhere. So that's it. Finally, print A if maximum of CNT is 0, otherwise print -1. Let me check against sample test case. Says that A is some int. It's a bit tricky here. Let me make it easier. Print A else print -1. -1, 1, 2. Okay, we have some error here. We have some error here. Okay. Candidate of X is M. 1, 2, 2, 3, 3, 3, 1, 1, 1, 1, 1. Okay, that's good. Let's submit code for Div. And it will not show AC, but you will soon see its AC when Codeforces is back. Actually, a contest is running right now and it's not judging our solutions. Let's solve problem E. For solving this problem, we need to solve 2 subtasks. Let's start with the first one. What we need to do first is how we can calculate A, the array A, to array, let's say, FA, as described in the problem statement. So, this FA array, for each index I, FA I should be mix of other elements in array A. So this is something you need to solve at the first. So consider K is 1. What is the answer? So first of all, let's solve this. So you can pause the video right now, think about it, and come back when you solve it. So yeah, now let's solve this problem. For each element, there are 2 cases. Let me say this is array A, and we have some element here. First of all, calculate mix of the entire array. Name it M. So M is the smallest value that you can't find in A. Okay. So there are 2 cases. Consider this is X, and we want to know what we need to put here in FA. Okay. If X is more than M, answer is obvious, right? What? Because there is some element less than it that didn't appear anywhere in the array. So for sure, this is gonna be M. Then, if X is less than M, note that X can't be M because M is not appeared in the array. So consider X is less than M. We know that we have X. We have X actually. So there are 2 cases. This element, the ith element, is the only occurrence of X in the array, or there is some other X here too. If there is some other X somewhere else, if there is some other X somewhere else, the answer will be, I forgot the solution a moment, but now I am again back. So if there is some other X, you can see that if we don't consider this X, we have all numbers 0, 1, 2, 3, 4, 2, M minus 1. So this is gonna be M. Otherwise, If that's not the case and there are more than one occurrence, there is only one occurrence of x, for sure, if we remove x, there is no other x's, and then it's x. So the summary, if x is more than n, or x appeared more than once in the array, it will be converted to m. Otherwise, it will remain x as it was. So that is about mix. So now we know how to convert f to f, how to convert a to fa. So now try to solve the problem for k's more than 1. Let me come with some hint. Start writing down some array A. Try to convert it to fa, fa, and so on, and see what happens. This is it. So try to do it like 2, 3, 4 times to see what is happening. So let me come with some guess, and then we'll see if our guess is working or not. So here you can see k is very large. And k is very large. One of the typical ideas you need to use is arrays are gonna repeat after some time. So that is actually what happens in this problem. Let's start with a very simple array which consists of just a single zero. It alternates like 0, 1, 0, 1, 0, and so on. Like if it was 2 zeros, it was like this. Okay. So knowing this, I suggest that after just a few steps, we'll prove that later. After just a few steps, we will see that our current array is the same as 2 steps before. When that's the case, we will find k where it's located and measure this distance. If the distance is even, that's the answer. Otherwise, this one is the answer. Like, let's say this is 0 step, k0, k1, k2, k3, k4. Like here you can see 2 and 0 are equal. Array at the step 0 and 2 are equal. Consider I want to find the answer for k equal to 4. That's easy, right? Distance between 2 and 4 is even, so this is the answer. That is correct. So consider I want to find the answer for k equals to 55. Answer is odd, so this is the answer. Distance is odd, so this is the answer. Let's code. Let's write code for this problem. N and k. N on k. Then array A. Then let me define a function here, f, which takes a and returns the array f. First, let's write cnt is counter of a, then return and then I need to find mix 2. So let's write mix is 0 while cnt of mix is there. So how does it work? Mix, then mix, then let's add something to mix. So this should work too, right? This works too, right? So return mix if x is more than mix or cnt of x is more than 1, else x for x in a. So this function calculates f for us. Then let's start with this. and while length of steps is less than 2 or less than 3 actually, or steps minus 1 is not equal this steps minus 3, continue this f of steps minus 1. And finally, we know that now they are repeating, like the last element of steps is equal to the third last. So now if first of all, if k is less than length of steps, that's a print steps k let's not make it very hard. If k minus length of steps glue 2 is 0, then we need to print the second last, else we need to print the last. We can merge these two things actually with like doing some math here, but let's not make it very complicated. Let me run this code 0 to that's just for sum. Okay, print sum of this, sum of this, sum of this, 318 25 0. That's very good. Problem E, and submit. Let's submit it. Just a note here, our codes for B, C, and D got AC. So yeah, we got AC of those problems. Let's wait for these to judge. While it's judging, let me tell you why this works and why it will repeat very, very soon, no more than 3 steps. So first of all, we have an array. After one step, you will see some 0, some 1, some 2, blah, blah, blah. And a lot of m's, which is makes up this array. And there is no element more than m. So there are some single elements, some unique elements after the first step. You will have some unique elements, they didn't appear twice in the array. And you can see a lot of m's and you will see nothing more than m. That's it. Then after another step, so we got AC. After another step, you will have some m prime here, right? The mix of these new array. Now you will have some 0, 1, and some m prime, which repeats a lot of time. Like you can have a lot of m primes. So you have 0, 1, 2, 3, and 2 m prime. Like you have m prime minus 1 once, m prime minus 2 once. You have all these elements at once, and you will have a lot of m primes. So after that, it converts to m prime plus 1, and it again converts to m prime. And you can see that after doing 3 steps, it will start repeating. So that's all about problem E. This is getting more complicated. Let's solve problem F. To solve this problem, first of all, for sure, what we need to do is being able to calculate F for 2 arrays, let's say A and B. So consider that we don't want to calculate F for all of the subarrays. We just want to calculate F for 2 arrays. That's it. So it's good to think about it for a while. You can pause the video. So now, let's say we have an array A and array B, and we want to calculate their F. Consider an element consider that here is x and here is y. If there is an element to the left of x, let's say m, where m is more than x, we can change x to y. Otherwise, we can't change x to y, and we should leave x as is. So, for each index, check if either ai is equal to bi, or there is some aj larger than or equal to ai, where j is less than I. If that's the case, add 1 to ans. Okay. So just add 1 to ans plus. So this is for calculating f. Now, what we need to do is finding this, and this can be found, right? Calculate the partial max from right to left. If partial max of this side, actually this element, is more than or equal to x, we can make sure that there is some aj more than ai, that j is less than I. Otherwise, there isn't. So given this, now try to solve the full version of problem that answers for all of the subarrays. For sure, you can pause the video here. So now let me try to tell you the solution, the full solution. Okay, given what we know here, I give you some other problem to solve. Consider we have an array consists of ones and zeros. Problem asks us to find sum of lengths of subarrays that start with a 1, some 1, and end with some 1. Sum of lengths of subarrays that are like this. So there are many ways to do that, but let me focus on a single solution. For each index, count the number of ones, and another condition is that length of subarray must be more than 1. So let's, for each index, count the number of ones to the left and the number of ones to the right. Answer will be sum of this number for all of the indices. So for this, 1 times 2. For this, it's 1 times 1. For this, it's 2 times 1, 2 times 1, and 0 for all of these things. So the answer for this array is 2 plus 1 plus 2 plus 2, which is 7. So what we used here, the trick we used here, is double counting. Double counting means you are unable to count something in some way, but you count it from some other aspect. Like, you want to count something, you can't do this like this, but why not trying to count it like this? So here, each subarray, let's say like this one, consists of some elements. Instead of counting each of them, counting each subarray length, we can find for each element how many subarrays it will appear in. And I made a mistake here, actually, because for this one I need to say 1 times 2, 2 to count these things. And also for this, I need to add something more. We need to modify the definition. Let me think a bit here. 1 times 3. Yeah, let's count subarrays that are just a single one, and then this is 1 times 3. This is 2 times 2, and also this is 3 times 1. So basically, I count ones to the left and ones to the right. How many ones this one has to the left? 1. How many ones this one has to the right? 3. So it's 1 times 3, 1 times 2, 2 times 2. Because 1, 2, 1, 2. So 2 times 2. So for zeros, that's easy. For 1, 3 times 1. An answer will be something different, no, not important. So what we are gonna do in this problem is the same. We will instead of trying to calculate f for each element, for each subarray, let's do a different thing. For each element, count that for each I. Count that how many times it will appear in some f. Let me try to help you understand this. Okay. Consider this array. These two arrays. This is I. Sorry. I want to count the number of subarrays that this I is adding plus actually in f of this subarray. Let's start this an easy case. Consider that AI is equal to BI. That's easy, right? So it will add 1 to all of the subarrays include this I. How many subarrays include this I? You can easily calculate number of them, which is I plus 1 times n minus I. So if AI is equal to BI, then we can directly add to answer this thing. I plus 1, n minus I. Otherwise, this I will add 1 to f of a subarray if and only if there is some aj to the left that is more than AI. So pause the video right now, try to think about the rest of solution. So how we can count the number of subarrays that this I has some j to the left that is more than or equal to I. First of all, the right border, the ending of the subarray doesn't matter, right? So if I is adding to this subarray, I will add to this subarray too. And the same goes for this one, right? So this is not important. So ending is not important. We need to focus on the beginning of the subarray. Beginning of the subarray must be somewhere that there is some aj more than or equal to ai. So you know the solution. Find the first element to the left, let's say aj, that is at least ai. Every subarray that starts from j and before that, like from 0 to j, is okay for us. So if we find j, we will add to answer j plus 1 times n minus I. That's it. That's it. Just something remains. How we can find the first element to the left that is greater than or equal to AI. For that, watch our NSJ video on this. So I'm gonna code it up directly. Let's see if we can solve this problem using Python. We can, I think. Okay. Let's read test cases. Let's read N. Let's read A. Let's read B. And now, let's find next for each element of A. So I consider that you already watched our NSJ video on this video tutorial. So next of each element will be the first element to the left that is greater than or equal to AI. So I defined next, which is -1 at the beginning for all the elements. Then I do a for loop. Then I set, we can do something better here, actually. I -1 for I in range N. Now while nxt of I is not -1, if it's -1, that's it. You watch our NSJ video, you'll understand what I'm doing right now here. While nxt is not -1 and nxt of I is less than AI, we want something that is greater, okay? And do nxt of I be nxt of I. Now we found nxt's and we are ready to calculate the answer. Let's do a for loop on I. Now ans plus equal what we have on our board here, okay? Nxt of I plus 1 times n minus I, but we need a modification here. If AI is not BI, else it's I. So if AI and BI match, that's very good, and we can have all the summaries, that's it. Otherwise, we'll use nxt. Note that if there is no nxt, it will be -1. -1 plus 1 is 0, and that will read to 0. Okay, let's print the answer. Let's test it against our test case. 5, 35, 26, 0. Okay, we have some issue here because it's 28. It's printing 28, but the answer is 24. Okay, let me focus on this test case. Okay, how to debug. This is large test case. Okay, we are counting something more than expected. So let's print how much we are adding to our answer every time. So it's adding 0, which is correct. Then it's adding 10, which is 2 times 5, that is correct too. Then it's adding 4. I made a mistake. Sorry. I made a mistake here because I said that there is some AJ more than or equal to AI here, but it doesn't mean necessarily that you can replace this with this. What we need to make sure is we need to find the first element to the left that is more than or equal to BI. So we need to find the first element to the left of this element which is more than or equal to BI, not AI. And then we can replace this element. That's why the code is giving wrong answer. Let me think a bit. We'll continue. Great. If you already watched our NSJ video, I tell you that there are some cases that still we need a stack. So that is one of the cases. You still need a stack here. So let's use a stack. I'll show you why and how. So what we need to do is keeping a stack here that points to the next greater element, and so on. And we'll binary search on them to find the first element that is at least bi. Then we'll find the answer. So let me count this stack while stack and a of last element in the stack is less than or equal to me. I'll do stack.pop. It will remove the last element, right? Yeah. And finally stack.append I. We will have finally, if AI is equal to BI, directly add I plus 1 times n minus I, else we need to do binary search to find the first element that is at least BI. So, and for sure we can consider the AI itself. Wait, if there is someone to the left that is more than, if this element is more than or equal to BI, I can directly change it to BI, that's it. If there is some element to the left that is more than BI. Yeah, so there are some other cases too. So if AI and BI are equal, we are happy, that's it. If AI is more than BI, we need to find the first element to the left that is more than AI. If AI is less than BI, we need to find the first element to the left that is more than BI. So that's enough that we just search for B. So our stack is decreasing. So we expect that first element is first element of a stack, the stack 0 must be more than or equal to BI, otherwise we will not find any subword. If that's the case, let's start this low and high, which are 0 and the length of a stack. Low is true, high is false, while high minus low is more than 1. Let's take some mid. If A of the stack of mid is more than or equal to BI, we are happy, and low is equal to mid. Otherwise, high is equal, we'll set high to mid, and finally low is the rightmost element that is more than or equal to BI, and we'll have this and plus equal stack low plus 1, because we can pick that 2 times n minus I. Let's run it again. Oops. Much more than before. How I ruined this? How I ruined this? Wait. Print I and this thing to see what happened here. 0, 6. No, for sure. There is an issue when This is weird actually. So for 2 it's okay, but for 3 is not, for 0 is not. So let's see, for 3 it needs to be 0, but it's 6, and it's because it's counting the AI itself. And for 4 it's counting. Let me think to fix the bug at once. So for 3, for this index, is 12 correct? Like we can't convert 6 to 5, right? We need to find something that is more than max of AI and BR. Those things are already more than them. So should never come to the last element of the stack actually, because it's the I itself. So let me run it again. It decreased it a bit, but didn't work a lot. So I'm finding something. So 12 comes from 4 times 3. I don't find this one actually. I think I found the bug. If stack low is less than I, do this, otherwise don't do this. Okay, we fixed the bug. Seems we are good to go. Let me come with some huge test cases. 530, 526, 0. And finally we have 0, but it's 1. It's 1 because I think that we shouldn't pop the equal elements here. 505, 20. Okay, this seems correct. Let me submit and see what happens. Problem F. This is our code. Submit. Let's see what happens. I'm a bit unsure about this solution actually. Let's come back and try to think about it. So it seems like we need to find something to the left that is more than AI and more than BI, and everything to the left is actually more than AI. So we need to just to make sure that they're more than BI. And okay, we got A. Okay, I will soon come back for problem G. Just fast and simple. That problem is super great. This is a very nice problem. I like these kind of problems so much. Before you start, this problem has a prerequisite problem. So if you are unable to solve problem 35C, let me make sure. Yeah, if you are unable to solve problem 35C, you shouldn't continue this video. So first, go solve problem 35C. Now, we consider that you know how to keep a graph. We consider that you know BFS and all. Now, let's solve this problem. Let's start with a case that we know the state of graph, and there are no queries. Like we know that some vertices are red, some vertices are blue, and we want to know for each vertex that if it's loose or V. That is a normal, like completely classic game theory problem. So that even this is the classic game theory problem. So the first problem people solve in game theory. So we can solve it like we have a DAG, right? Blue and red. So red vertices are loose for the first player and bin for the second player. And in this problem, you need to keep an state which is V and T. V is the vertex, T is turn, which is 0 or 1. 0 shows that this is the first player's turn, and 1 shows that this is the second player's turn. If V is a red vertex, for T 0 or 1, it doesn't matter. The result is the second player will win. So let's name the array DP, but it's not like DP. So we set it to 1. So DP is a Boolean thing. It's 0 or 1. 0 shows that the vertex is 0 shows that this state, if we are in this state, the first player wins. 1 shows that the second player wins, and so on. Yeah. Now, for other states, consider that we have some V and 1, and there is a U and 0 that we know that V has edge to U. If this leads to player 1 to win, DP of this will be 1, 2. If there is no way to win, I mean all of these U zeros lead to 0, then this will be 0, 2. So to make it more clear, for a Vx, consider all vertex we have like Ux, let's say U1, U2, X, and all. If there is single one of them, it's 1 minus X. So the next turn will be for the other player, so 1 minus X. So if there is one of them leading to winning X, for this state, winner is X2. Otherwise, winner is 1 minus X. So that is solution for when we don't have queries. We just have one DAG and we want to answer one state. So actually, what we found can solve problem in OQN. QM actually. And how we can do that? We do topological sort. We start from vertices from bottom to Oc and solve for each vertex for V0, V1, what's the outcome, and that's it. Now, the situation is different. We have some queries. And how we can solve queries. For solving queries, let me tell you what we can do for solving queries. So, at the beginning, all of the DPs, let's say DPs, all of the results of the vertices of the game is 0. Like for each Vx, DP of it is 0. But for each query, after each query, we change a node to red. And when we change a node to red, now DP of that vertex 0 and 1, DP V0, DP V1 becomes 1. So the second player, Madhu, wins. Then we need to apply this on other vertices. This is when it's important. This is the tricky part. So we know that DP of some state changed. We need to cascade it into other states. And what happens? So consider that we have a V1 and the answer for it, let's say dp of it, was 0. Once one of its, let's say children, it's not children, but let's say children, changes from 0 to 1, this comes to 1, 2. So our first condition is, if we changed, so we only change dp's from 0s to 1, we never change a 1 to 0. That's obvious, right? So when a dp of a vertex is changing from 0 to 1, we check for all of its it's not parent, but let's say parents, and if they are x, and we change their dp v1 to 1 like this, if it was 0, and it can be cascaded. It can be cascaded. And there is another case. Where we have a z0 here, and the answer is 0. Do you believe that if I change this thing that was 0 before to 1, it will change this 0 to 1 too, like what happened here? No, for sure, because it may still have some other 0. But it can eventually make it 1 if we change all of these things. So to keep that, we need to keep for each vertex number of children, let's say, it has that are currently 0. And when one of them change to 1, we do for that minus minus, and if it reaches 0, we'll change dp to 0, that's it. A side note here is, unlike many games that we use dpv like lose and win, we can't use here because it's single state, can be win for both players or can be lose for both players. It depends on who is playing. Like a very easy example of this is this graph. So when we are at this, if it's the second player's turn, he will win. If it's the first player's turn, he will win too. So this game is not like our normal games that players are identical with each others. The first player and second player have different goals, so they are different. And yeah, so I think that we have all the idea we want to have. I will review the entire solution from the beginning to end again. So we define a dp. dpvx is at the beginning 0 for all, is all 0, or let's say false. So actually it's gonna show us if second player will be. And so dpvx means that if second player Madhu will win. It's at the beginning all false. Then when queries they come, we change a dp to 1, and then it's like a DFS. It will cascade to other states too. How it cascades? When we are changing a 0 to 1, we'll check all of the vertices who has edge to this vertex. We'll change their dp v1 to 1, 2, and we'll decrease their out degree, their, let's say, win degree, something like that. Let's define exactly Gorham's win degree. Gorham win degree. Let's fix the array name. We'll decrease the Gorham win degree by 1, and when Gorham degree is 0, that vertex will be 0. But why time complexity of this is good? Time complexity of this is good because for every vertex, once it will change from false to true, And because of that, what we do is OQ plus. And let's jump into code. And let's start coding. Let's start this reading the number of test cases. Then this will keep our graph. This will okay. Let's start this. Let's now read heads. Okay. Now let's read queries. Then let's if x is 2, we just need to print the answer. This is gonna be Boolean. The first player starts at vertex u minus u. That's it. Else, let's update u. Now let's define function update. Here we need to add Goromvin degree of v2. Okay. Now void update. Now int viv if and also turn is important. Let's say player. And here we need to do update u0, update u1. It's very hard here to choose between true false and but I choose to use Boolean. If this is already 1, just return. Otherwise change dp to 1. It means that the second player will win. Then I'm gonna go over all of the vertices has edge to these vertices, and then I will update u for the turn of for the second player's turn. If it's second player the exit, we'll update it directly. Then if minus Goromvin degree of u is now 0, then I will update this with the first player 2. So that's it for code of this problem. Before we kneel, let's reset everything. You will fill all the indexes and pause and this empty vectors. And then we will fill all the Goromvin degree to Boron degree plus and with 0. Then we'll fill DPs. You'll fill DPs before this false. DPs to DPs are And let's say like this, dp of 0, dp of n. It will fill everything with 0. We have nothing left, okay. What is it saying? But the recursive, no worries. Let me copy paste. Oops, I think this is a huge test case. And run this thing to see. Oops. And we have some errors in my CMake list, sorry. And okay. Okay, let's run again. Let's run again. It's still building, running. Okay. 0 1 1 1 1 0 0 0. I see some wrong answers. Actually, we should print yes and no. So if dp, we should print no, otherwise we should print yes. Let's see what is our problem. So yes, then no, then yes. This is an error. Okay, this is the, we have just one error. Let's focus on that. We have 8 edges, right? And queries of type 2 are for, so 1 2 3 4 5 6 7 8. This isn't their predicons. And this is that query, I think. Let's remove everything else, then run it again. Yeah, it's a bit tricky one. Okay, let's change it to 5 to make sure everything works correctly. Oops. Okay. Yes, no, no. And while it needs to be yes, no, yes. Okay, let me remove this and then this too. Second query was asked, right? Okay. So let's change it to treat. Answer should be yes, but it's no. Okay, now we can focus on what's happening here. Okay, this is our graph. 3 and 4 are now red, and we start playing on 2, and for sure we have choice to, yeah, the answer is for sure yes. And so what is the problem here? So the problem here should be at some time like this Garam win out degree gets too low. That makes problems for us. Oh, I understand. We made a mistake actually. We made a mistake. Actually. So, yeah. Okay, got it. So the mistake is here. And because I should go to the opposite player, not the, like this is not what happens. Okay. So if player, if this is a first player, just go update, that's it. Otherwise, if it's the second player's turn here, so yeah, I think now it should be correct. Good. Let's do it again. Seems good. Everything seems good. Ready to submit. Let's submit the code. Okay, we are experiencing. Okay. Or is I could submit directly here. Okay. That's it. We submitted, but blocked by Cloudflare. So let's verify I'm human. Then let's submit again. Okay, we got AC of all problems in this third division contest. It was very fun. It was very interesting contest. I enjoyed all the problems actually. Especially problem J, that problem G that is exactly mid-type. I like this kind of game theory plus somehow DFS BFS problems. I hope that you enjoyed this up solving session 2. See you soon, maybe in the next up solving sessions. Bye bye.